Okay. Last time we have solved problem number 2 and the problem number 4 and problem number 8 concerning the voltage regulation. Today we are gonna solve the problem number 6 because it's include a lot of issues concerning the transformer, which transformer test, phasor diagram, voltage regulation, parameters calculation, or all what we have seen in the transformer is applied in this problem. So problem number 6, a single phase transformer, 100 kVA, 1100 volt gave the following test results. So in the open circuit test, those are the measurement in the open circuit test, voltage, current, and the power. And for the short circuit test, those are the measurements. So we can see that the open circuit test, the high voltage side was open. So they take the low voltage side as primary. While in the short circuit test, here it's mistake. It's shorted, not open. So in second test, the low voltage side is shorted. So they took the high voltage side as primary. So we don't confuse in this. So we have high voltage and low voltage side in the transformer. Each one of them can be taken as primary or secondary. So the primary always connected to the source. As the secondary, it's depend. If we have a load, it's connected to the load. If we have a test, either it's open or shorted. The question number 1, determine the rated voltage and the rated current for high voltage and low voltage sides. Calculate different transformer parameters, then drive an approximate equivalent circuit referred to the HV side. Determine the voltage regulation at full load, 0.6 the power factor leading. So here it's leading power factor, and draw the phasor diagram for condition C. So in case of leading power factor. So the first question is the rated voltage and rated current and the rated voltage of high and low voltage side. So let's go back to the data. Here we have the apparent power S, we have the high voltage and the low voltage. So according to this data, the high voltage is directly the voltage. Let's V high, for example. The high voltage is 1000 as given here, while the low voltage is 100. So the current, in case of the current of the high voltage side, not the high current, the current of the high voltage side. We know that the current and the voltage are opposites. So the current of the high voltage side, IVH, for example, is equal to what? Equals to S over VH. And it's equal to what? To S is 100 kilo. So it's 100 kilo kVA. So it's 100,000 kVA over 1000. So 100,000 over 1000 equals to 100. So this is the current of the high voltage side. While the current of the low voltage side equals to what? Equals to S, apparent power, over the voltage of the low voltage. So it's 100 kVA over 100. So it's equal to 1000. So wherever the voltage is high, the current is low, and wherever the current is high, the voltage is low. So the current in the low voltage side is bigger than the current in the high voltage side. Okay, so this concerning the first question. So here the rated voltage and rated current for the high voltage and low voltage side. So the voltage of the high voltage is 1000. So the current of the high voltage side is S over VH and equals to 1000. The voltage in the low voltage of the low voltage side, so the current is S over 100, so it's equal to 1000. Now let's calculate the transformer parameters. Firstly, from the open circuit test. So which are the parameters that will be determined from the open circuit tests? We have of course RC, and we have XM, and we have the voltage, the turn ratio, which is V1 over V2. Okay. So RC, the resistance that represent the core losses, equals to what? Equals to V over IC, which is the current of that represent the core losses, and equals also to V square over P0, which is the power in the no load or in the open circuit test. So let's go back to the data. So the power in no load test is 400. Therefore, the RC, the resistance, equals to what? Equals to 100 square, which is the voltage of this test, given in this test, over 400, and equals to 25 ohm. So in order to find the XM, so let's go to the table. In the no load test, generally we neglect the resistances and the reactances of the primary and the secondary. So we have only the core losses resistance and the core loss, the magnetizing reactance. Okay. So the current here, I0, 0 indicates to that it's no load test, and V0 or V. And we have, of course, a wattmeter that measure the power. So the current here, I0, which is the no load voltage, get divided here into IC, which is the current of core losses, and IM, which is the magnetizing current. So I0 equals to IC plus IM, but vectors. Okay. But vectors. Okay. So IC equals to what? IC equals to V over RC. So it's RC here. So it's equal to 100 over 25, and it's 4 amp. And we know that I0, which is the no load current, equals to IC plus IM vectors. Therefore, IM equals to square root of I0 square minus IC square, and equals to 6 square, square root of 6 square minus 4 square, and it's equal to 4.47. Then we can determine XM equals to V voltage over IM. And also XM can be calculated if we have, for example, the reactive power equals to V square over Q, if we have reactive power. So the current flowing through the resistance is the IC, the core losses current, and IM is the magnetizing current that flowing in XM, which is the magnetization reactance. Okay, this concerning the second question. Now the transformative ratio, of course, directly equals to V1 over V2. So 100 equals to 1000 over 100, and it's equal to 10. Now, from the short circuit test, we can measure R short circuit, which is R equivalent, and we can measure X equivalent, and of course Z equivalent, and also the copper losses. So the copper losses are almost equals to the short circuit power. So RC, which is R equivalent, which is almost the short circuit resistance, equals to the power measured in the short circuit test, PSC, P short circuit, and it's equal, by the way, to the almost, if we neglect completely the core losses in this test, so the short circuit power will be equal to the copper losses over the short circuit current square. Here before proceeding, let's go back to the measurement here to the data. So here the shorter circuit test has been done in what? So the low voltage side is shorted. So the test has been done in the high voltage side, and the rated current of the high voltage side is 100. So here also is 100. So here the short circuit current is the rated current. So is the rated current. So the R equivalent equals to 0.18. Now Z equivalent, which is equal to the short circuit's impedance, equals to V short circuit over I short circuit. So always in the short circuit test, the voltage is reduced. Okay, is reduced. Here we are in the high voltage. We are in the high voltage side. So the voltage is too low compared to 1000, which is the rated voltage. Here we are looking for the rated current, not the rated voltage. So the voltage always is reduced in the short circuit test. So Z equivalent equals to 50 over 100, and this equal to 0.5. Now Z equivalent, of course, equals to X equivalent equals to square root of Z equivalent minus R equivalent square. So this is the value of X equivalent. This concerning the parameters. So RC, XM, and R equivalent, Z equivalent has been determined in open circuit and short circuit tests. Now, approximate equivalent circuit referred to the high voltage side. So here they didn't specify if it's primary or secondary. Here, to be more specific, it's better to say referred to the primary or referred to the secondary, to be more specific. But when they say high voltage side or low voltage side, it's up to what we have choose as primary or as a secondary. In this test, we can see that, for example, for the open circuit test, they choose the low voltage side as primary and the high voltage side as a secondary. In the second test, they reverse it. Okay. So here it's better, as I said, it's better to specify normally in the problem. It's better to specify primary or secondary, not high voltage or low voltage. But here let's consider that the low voltage side is primary and the high voltage side is secondary. So why the specific, the approximate, not the exact? The approximate equivalent circuit is the most simplified circuit. What does it mean, approximate? So when we move the parallel branch, to the input. So this is the circuit. So we have X equivalent, we have R equivalent. So since it's referred to the secondary, so this is the voltage of the secondary, V2, while the voltage of the primary, V1, will be divided over A. Okay. And this one is X equivalent, and this one is R equivalent. Also, of course, we have the parallel branch here. We have the parallel branch here and here. Okay. So why we choose this circuit exactly? Here we have R equivalent and X equivalent. When we move the parallel branch, we can add the resistances and reactances of the primary and the secondary to each other. So if the circuit referred to the primary to the secondary, R equivalent equals to what? Equals to R1 over A squared plus R2. So we can do this addition only if we have an approximate equivalent circuit. If we have exact equivalent circuit, we cannot. That's why mostly we work with approximate equivalent circuit. So of course this is the current, which is I2, and it's equal to I1 times A. And also we choose this circuit to help us in the next question, which is the voltage regulation. I hope this is clear before passing to the next question. Okay, we have a lot of Okay, so for the problem, high voltage or low voltage, I said to be more specific, they should give you which is the primary or which is the secondary. Okay, but when we work in one side, either primary or the secondary, we don't mix. Our calculation will be right. Okay, because it's the same transformer. Take it from this side or take it from this side. It's the same. So, but we have to respect. If we work on the primary, we should work with always. We should work with a single side. But for me, okay, I said it's be preferred to they specify to you. For me, I will specify to you which is the high voltage or the low voltage side. Okay, so we have primary, always the one is connected to the source, and the secondary is the one is the one connected, for example, to the load. The high voltage or low voltage in the transformer design, the side that has more turns, turn ratio, turn number of turns, of course, it's the high voltage, and the side has lower turns, it's the low voltage. But this, if they give you, for example, the turn ratio, you can guess if they give you, for example, the turn ratio. But it's if they didn't give you the turn ratio, they didn't say that it's step down. Sometimes they mentioned it's step down or step up. So there are many ways to know which is the high voltage or the low voltage. For example, we can say step up directly, step up. So it's the primary is the low voltage and the secondary is the high voltage. If they said step down, it's the vice versa. The primary is the high voltage and the secondary is the low voltage. If they give you the turn ratio, we can guess the side that has more turns is the high voltage, and the side that has low turns is the low voltage. Otherwise, they must specify. Okay, for me, I have to specify which is the primary and which is the secondary. In this problem, high voltage side we chosen as a secondary, not primary. So when we go to the secondary, we divide the voltage over A. Okay. Let's continue. Now, as I said, we have used the approximate equivalent circuit. Now, determine the voltage regulation at full load with PF is 0.6 power factor leading. Okay, so we have seen in the problem number 8 different cases when we have a lagging or leading or a unity power factor. So we know that the voltage regulation is the what we can see. It's a difference. Okay, between the magnitude of is the change. We can say it's the change. Okay, because it's delta V over V. It's the change in voltage magnitude before and after connecting the load. So we had a problem with this last time when we said no load voltage. When we specifically here, when we are talking about the voltage regulation, it's not means that we are in the low load test. Okay, the no load test can be done with the rated voltage and can be done with another voltage, not necessarily to be the rated. But here, when we are talking about the no load voltage, it's after and before connecting the load. So the voltage regulation show the effect of connecting the load to the transformer. So it's depend on the type of the load, the voltage will change, will maybe increase, maybe decrease. Okay. Okay. Okay, let's don't be confused. You said that the secondary. Okay, hold on. You said that the secondary, we have 100 volt, and in the primary we have 1000. Okay, let's read the problem again. Okay, so here. Okay, here we have 1100. It's not specified which one is. Okay. Here, open circuit test. The high voltage side is open. Okay. So the high voltage side is the secondary. Is open معناتها secondary because we connect our measurement devices and the source in the primary. Okay, so here the high voltage has been chosen as secondary, is open. So HV is chosen as secondary. Okay, look, man, there is no, it's not that it must be, this one must be primary and this one must be secondary. It's depend, it's your transformer. You came from this side or came from this side. Yes, okay, so here, for example, open circuit test, HV side open, which means HV is secondary because we let it open. Here, short circuit test, LV normally, LV is shorted. Here, LV is the secondary. Okay, so there is no something to oblige you to make this primary or make this secondary, except if they mentioned directly, if they mentioned this one is the primary and this one is the secondary. Here it's not specified completely. Okay. I said we can consider that you have to separate. Okay, you have to separate between. Okay. So okay, but when you calculated, we got 10. So we said that we calculate here. Okay. Yes. Okay, we have to separate. Okay, please question by question. Okay, when we say that we have an open circuit test in the secondary, look, okay, if you said that we have a test in the secondary, so that secondary became primary, okay, because where the primary is where you place your source, okay, the voltage source, where you place the voltage source is the primary. Okay, so when you said that we have a test in the secondary, that means we connect the voltage source to the secondary, so that secondary became primary. Okay, so it's clear, as someone of you said, it's clear as long they specify to you which one is the primary, which one to the secondary, and you have to separate between the meaning of the primary and secondary and the meaning of the voltage side and low voltage side. So high voltage and low voltage. Okay, look. Okay, let me finish this idea and I will back to your question. So, okay. High voltage and low voltage is depend to the design. We said that the side that has higher number of turns is the high voltage. Okay. While the primary or the secondary is our choice. Where we place the voltage source is the primary. Okay, and where we connect the load, for example, is the secondary. Concerning your question, Sarah, when we say that we have open circuit test in the secondary, which means, no, we cannot say it's in the secondary. Because if we choose that side, it will become primary. Yes, RC and XM is the same, but when but RC and XM are in the primary. So when you go to the secondary, you have to divide them over a square. Jama'a, let's organize our ideas. Okay, I will repeat from the beginning. Okay, idea per idea, so don't get confused. Okay, Firstly, we said that high voltage side and low voltage side, it's depends on the design. So the side that has greater number of turns is the high voltage side. The side has lower number of turns is the low voltage side. Now, which one is the primary, which one is the secondary, is our choice. Because we can choose this one as primary when we connect our. Because the same transformer can be used as step up or step down transformer. Okay, so if we choose the high voltage side as primary, so we are going to reduce the voltage. If we choose the low voltage side as primary, we are going to rise the voltage. So it's our choice. Concerning RC and R and XM, RC and XM are in the primary. Why are in the primary? We have seen that apart from the current of the primary flows through the core, the parallel branch. So RC and XM are in the primary. When, for example, when I ask you to give me equivalent circuit referred to the secondary, that time, please don't write question. I'm still talking. Okay. That time, so for concerning RC and XM are in the primary. So when I ask you, for example, to give me a circuit referred to the secondary, you need to divide RC and XM by A square as any resistance, as R equivalent, Rx as X equivalent. Okay, so we need to separate those two meanings. Okay, Rona, Z equivalent we found from the short circuit. It's depend if we were in the primary or in the secondary. Okay. Yes. But the value of Z equivalent, it does not change if we are in the primary or if we are in the secondary. What change is R1 or R2? But yes, if we are in the primary or in secondary, because the result gonna be R equivalent equals to R1 over A square plus R2. Yes. Yes, but Z equivalent itself. Yes, yes, Mahfoud. The computation of RC and XM are done, okay, for example, logically, logically, when I have transformer cell. So if I connect the voltage source to this side, for example, to do the open circuit test, just if I connect the voltage source to this side, class, that side is the primary, because I connect the voltage source. That's it. For Z equivalent, yes, the expression of R equivalent may change, but the value of R equivalent does not change because it's the same transformer. Okay. RC and the XM, yes, 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 because they are تابعين primary. Okay, Mehdi, if we take LV or IHV as the primary, yes, A, it's become A or 1 over A. Okay, but it does not mean that it will change something. Okay. Okay, let's continue. Inshallah, when we get back this problem exactly of the transformer, we are gonna. Okay, so what about XM in the secondary? Not like in the primary. Okay, they are the same, but when we put them in the secondary, we have to divide them by A over 2, because originally they follow the primary. تابعين primary, not to the secondary. So if I sent them to the secondary, I must divide them by x الاخر x by a square. Okay. 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 In the open circuit test, the value we get is directly is xm, not xm over a square in the open circuit test, because it's done in the primary. The test is done in the primary. Why? Because it's a primary, because we done the test on it. So the found value in the open circuit test is xm and rc, not xm over a square and rc over a square. If they ask us to refer them, yes, it's always primary. It's a primary because يا جماعة بالعربية كي تقولوا لي we can't do the open circuit test in the secondary. احنا مادام درنا فيه تيست وهو ولا primary. Okay. Because خلاص مادام بلاسينا the voltage source, the secondary يولي primary. That's it. ما كاينش حاجه اسمه هذا directly primary وهذا اسمه secondary. It's our choice. مادام درنا فيه التست يولي primary، خلاص ما ولاش اسمه secondary. اوكي صح، high voltage و low voltage it depends to the design. But if we done the test on it in the second question. Okay. Here it's HV side. Okay. The confusion. Okay. Here, according to what we have done, we have done everything in the primary. Okay. Okay. So let's. Okay. Like this. So here we have specified because we have done everything in the primary. Look يا جماعة, I will repeat. When we said that we have done a test in the site, so wherever we place our voltage source is the primary. Okay, that's it. But when we talk about the high voltage and the low voltage, it depends to the design. So the high voltage, the side that has a higher number of turns, and the low voltage side is the side has lower number of turns. Okay. So for the calculate different transformer parameters, then drive the approximate. Okay. Here they ask just to calculate the different transformators. Then, okay. Normally this question will be separated. Okay. Here we have calculated the tests, all parameters in the primary. Okay, it's our primary, so okay. R equivalent and X equivalent. Okay. No, احنا عندنا R equivalent دوكا ما دخلناش في R1 و R2. Okay, because R equivalent it's conserved if سواء راهو connected to the primary or to the secondary. So R equivalent and X equivalent it's the same value. دوكا الداخل واش فيها R equivalent it can be R1 plus A square R2 or it can be R1 over A square plus R2. But R equivalent itself and X equivalent itself, it will be it's conserved whatever. But here, for example, شوفوا يا جماعة, for the parameters calculation, yeah, صح, it's okay. For example, we have seen that the open circuit test has been done in the H voltage side. It has been done in the low voltage. The short circuit has been done in the high voltage. But both of them has been chosen as primary. Okay. So here, when we calculate RC and XM, we are working on the primary. Here, when we calculated R equivalent and Z equivalent, also we are working in the primary. It's not the same side, but it's the primary. Okay, here we change the primary, but it's still the primary. Okay. To do not get confused, always draw your circuit. For example, هذا for open circuit tests. This circuit, we cannot say that it's referred to the primary or to the secondary. We don't care, even we don't care. I have voltage, I have current, I must to calculate RC and X. Okay. I know it's the primary because I give voltage here. في the short circuit test, this is my test in the short circuit test. Okay. I have R equivalent, X equivalent. Okay. I give voltage here. So I'm working in the primary. No need I give the voltage in the primary ومن بعد نهز الفولتج نتاعي ونروح نخدم في السكندري. Why? I have the primary, I work in the primary because here I choose the voltage. Primary when we وقتاش تدخل prime secondary, for example في الفولتج regulation شفنا ولا في sometimes maybe they ask you to give all the parameters, to give R1 and R2, etc. But here, if we were working with R equivalent and X equivalent, they are conserved, so in the primary or in the secondary. Okay, R equivalent. Okay. R1 or R2. Okay. R1 or R2 كاين approximation. We can كاين approximation. I will show it to you because okay. R1 or R2 can be found. Okay. Can be found يعني experimentally with a test called DC circuit test. So we feed the transformer with DC voltage and we measure the DC current and we do Ohm's law. We can find R1 or R2. هذه experimentally. Theoretically يعني approximately واش نقدروا نديروا to determine R1 and R2. For example, if we have R equivalent. Okay. If we have R equivalent, we can divide it by 2. Okay. For example, R equivalent is 100. Okay. So, okay, R equivalent is 100. نقسموها على زوج, it's become 50. So, if we are in, for example, the circuit is referred to the primary, so R1 is 50. R1 is 50. A square R2 is 50. Okay. For example, if we are in the secondary, R2 is 50 and R1 over A square is 50. So you need to find A square. This is an approximate method. Okay, مش exact يعني, but it's هكذا approximative. Is it clear? Yes, R equivalent, what is it's R1 plus R2 A square or R1 over A square plus R2 plus R2. Okay. So here the first one. معليش نعاودوها. Okay. This is R equivalent. Equals to what? Equals to R1 plus R2 A square or equals to R1 over A square plus R2. So this one, the primary, the secondary. Okay, so if we have the value to R equivalent, okay, okay. Okay, let's continue. So if we have R equivalent, and I want to have, I want to find R1 and R2. R1 and R2, we have an approximate method. An approximate method. So we can divide R2 over 2. R equivalent. For example, I said, let's consider R equivalent is 100. So if we divide it by 2, so R1, for the first case, R1 is 50. And R2, A square R2 is 50. Not R2, A square R2 is 50. So R2 is equal to 50 over A square. If we are in the secondary, R1 over A2 is 50. And R2 is 50. Okay. This is an approximative. This is an approximative method. Approximation, Barkim, it's not exact method. Okay, they should precise the site because hadith HV or LV, it confuses you. Okay. It's not any problems. It's not my problems, but I promise you, in your test or in your exam, I will specify to you. Okay. Manage. But even if we don't have, for example, غدوة عندك كونكور ولا ويعطوك exercise على الترانسفورمر. Even if it's not specified, you can choose anyone and work on it. You are free. And if your measurements and calculation are correct, you can do it even with 2 methods. You calculate in the primary and you can calculate in the secondary. Okay, but you should respect. You should respect the impedance transfer from the primary to the secondary. You respect the referred equivalent circuit from the primary to the secondary. That's it. ابسط حاجه هنا شفنا فور اكزامبل في الكالكوليشن تاع R1 و R2 الابروكسيميشن هذه it will give us, we give an example and it will give us same. Okay, inshallah when we get back we will have a session about the transformer again. I told you at the beginning this chapter is so important. Also this analysis is the same with the induction motor. مانيش عارفين نقدروا نشوفوا at least the induction motor كيفاش مداير. But this analysis is the same as the induction motor. حاجة واحدة برك induction motor ما عندناش turns ratio, عندنا another thing. Or everything is the same. Okay. So here for the okay, so I'm going back to the presentation. Okay, معليش. It's good to have a discussion, and no problem. Even if we have solved one problem, and we have a rich discussion, better than solve 10 problems. Okay. So here, so this is the calculation. Now we're talking about the voltage regulation. We said that the voltage regulation is the change delta V over V between the voltage no load and the voltage with load. We said that it can be calculated in the primary and in the secondary. Last time, the last session, we have seen a problem that we have solved. We have found the voltage regulation in the primary, and it can be found in the secondary, and it will be the same result. Okay. Always, I repeat again, choosing the side primary or secondary, it will not change your measurement. But you have to respect, if you work in the primary, you have to respect the impedance transfer or the secondary. Okay. So since the circuit is referred to the secondary, so we are working on the secondary, so the voltage regulation equals to what? Equals to V2 is the voltage across the load. And the V1 over A is the primary voltage referred to the secondary. And it's the no load voltage or before connecting the load. If we are working, for example, in the primary, this expression become like this. It's become V1 minus AV2 over AV2. And you will have the same result. Okay, but just we have to respect. We have to respect the side. Okay. Now, using the equivalent circuit, the approximate equivalent circuit, the simplified one. So this is the X equivalent. This one is the R equivalent. Here we have a load. Okay, we have a load, for example, whatever, we have a load. Also, here the parallel branch can be, its effect can be neglected in the approximate circuit because the voltage is the same. The voltage across the primary or across the parallel branch is the same. So we can neglect its effect. So this circuit is referred to the secondary. So we start by the secondary voltage, V2. So it's our reference, V2, because the circuit is referred to the secondary. This one, for example, is X equivalent. This one is R equivalent. R equivalent and is X equivalent, their values are the same, whatever we are in the primary or in the secondary. Their expressions may be changed, but here we don't need R1 or R2. Generally, in most of the problem or the cases, we work with R equivalent and X equivalent. We don't work with R1 and R2. Just if, for example, they ask you for them. But generally, we work with R equivalent and X equivalent. Now, if we do mesh analysis, for example, we see that V1 over A, which is the primary voltage referred to the secondary, equals to what? Equals to V2 plus the voltage drop. The voltage drop is I multiplied by Z equivalent. Okay, the voltage drop. And it's equal to what? Okay, since we have power factor 0.6, so the angle is 53, and we have taken it positive because it's a leading power factor. So we take the angle positive. Okay. Now the voltage drop equals to what? Equals to A2 multiplied by R equivalent plus JX equivalent. Okay. Let's just move this circuit here. Okay. So the voltage, of course, is 1000. V2 is 1000, and the current is, this is the angle of the current, 53, and this is the Z equivalent. Honestly, I'm not so good in calculation complex numbers, so you should verify those calculations with me. I tried to write it step by step. So if we write the rectangular form of the current is this is the value of the current in a complex form. Then this is the result. This is V1 over A. So here we said that the voltage drop can be positive or negative. Okay. So here the voltage drop were negative. Okay. So this is the no load voltage after connecting the load. Before connecting the load. So we can see here that after connecting the load, this voltage increased, not like the case of the lagging power factor. So I will repeat it step by step. So using this circuit, V1 is V2 is the voltage across the load. This one you should save it in your mind. V2 is the voltage, which is the load voltage, or the V2 is the load voltage or the load or the voltage across the load, plus delta V, which is the voltage drop, the current multiplied by the equivalent impedance of the transformer. So after doing those calculations, because here the angle play an important role. The sign of the angle, not the angle. Okay, the sign of the angle if it's positive or negative. So because it's a leading power factor, so the sign here chosen negative. Okay, so after those calculation, we can find that V1 over A, which is the voltage of the primary referred to the secondary, equals to, just a remark here, we work for the voltage regulation, we use magnitudes. Okay, so after finding the voltage, so here it's in a it's in polar form. Here it's in rectangular, but we take only the magnitude. So this is the voltage regulation. We can see that the voltage regulation is negative. So it can be written like this, or as a percentage like this. So we work with a magnitude. Is it clear before passing to the next question? Okay. So why we always, you can see that the equivalent circuit or the circuit analysis help you a lot to understand, to do not get confused in your calculation. Instead of that's what is good in this module, especially in the transformer. Instead of تولي تحفظ القوانين, you can use the circuit analysis and you can extract all what you need from the equivalent circuit. Okay, you have to be smart in this. You can use the equivalent circuit because we use the basic electricity laws. We don't have any integration, we don't have derivation, we don't have differential equations. We have basic electricity laws. Ohm's law, Kirchhoff's law, that's it. So you can use the equivalent circuit to extract what you need for your analysis. The last question is the Phasor diagram. The Phasor diagram. So this is the Phasor diagram in the case of leading power factor. So we're gonna do it together. Okay. So in case of leading power factor, always we said we choose reference. We have a reference, of course. Okay. We need arrows. Where is the arrows? Okay, I don't know where the arrows goes. Okay, those are the shapes, yeah. Okay. So this is, for example, the voltage across the load, V2. So, okay, let's put the circuit. So this is the circuit, R equivalent, X equivalent, the load voltage. And so this is V2. This is V1 over A. And this is the current, I2. Okay. So the angle, the current is shifted by the theta angle. Okay. So theta, the angle between the current and the voltage is the current of is the angle, is the global shifting angle. Okay. It may be different from the angle of the impedance, for example. Okay. So let's choose another color. So this is the current. So according to the angle of the current, so here it's positive. So this is the current, I2. Now the voltage drop, the resistance are equivalent. Multiplied R equivalent A2. The resistance, of course, does not have any shifting angle, so it will have the same phase as the current. Okay, so this is the resistance, while the inductance will be shifted by 90 degrees to the resistance. Okay, so this is the inductance. Of course, here when we want to draw a real Phasor diagram, you should respect at least the scale. Okay. Then this one is the voltage across. هو normally يجي هنايا ما يجيش ثم يجي لتحت شوية. So you need to respect the scale. Okay. Okay, should be like this. This is the voltage, the no load voltage, V1 over A. But in fact, it must be, according to our measurement, it's okay. According to our measurement, its magnitude is less than 1. normalement يخرج لنا أقصر من هذا. Okay, so I said you should respect the scale. Yes, when we draw the diagram, we take into consideration the values approximately, but you should respect. Okay, for example, here it's wrong because we know that V2 is more than V1 over A. This one is 1000. This one is less. Okay, normalement يخرج لك أقل منه شوية. Like you see here. Okay. At least. I will not ask you to draw it in millimetric paper, for example. Maybe, مانيش عارف. Okay. So I ask you to repeat this problem. This problem includes the most things we have seen in this in the transformer. I ask you to repeat it again and try to understand it slowly. Okay, let's move quickly to the. We don't have so much time because I have to move at 3:30 p.m. Okay, so let's try to solve this one quickly. Problem number 7. Okay. Problem number 7. Consider a 15 kVA transformer. The voltage here is 700. The high voltage is 7,500, and the low voltage here 480 voltage. So here the meaning, this distribution transformer. Look, if it's they mentioned it's distribution transformer, so it's directly step down. Okay, هذه شوف عليها مليح. If they said it's distribution, because in the distribution we pass from here in Algeria we call it the medium voltage to the low voltage range. Okay, so we move from, we have I told you before, we have different ranges. We have the very high voltage and the high voltage and the medium voltage and the low voltage. Okay, so if they said the distribution transformer, here it's specified. So if it's distribution transformer, it's step down. So here, this is the high voltage, this is the low voltage. So here, the high voltage side is the primary, the low voltage side is the secondary. Okay, distribution. فهمنا? Distribution transformer means step down. Okay. Yes. Distribution transformer هذوك اللي تلقاوهم سواء مبلاصين في لي بوطو هذوك but in fact هم 3 phase anyway, or those تلقاوهم في لي بوست هذوك. We have one here in INELEC. Okay. So consider 15 kVA 7,500 480 volt distribution 60 Hz distribution transformer. Assume that the open circuit and the short circuit test were performed on the primary side of the transformer. Okay, so both of them have been done in the same side, and that's the following data were obtained. So here both of them have been done in the same side. Okay, so هنونا the open circuit test on the primary. Okay, so those are the measurements. The question here: determine the impedance of the approximate equivalent circuit referred to the primary and to draw a corresponding the simplified equivalent. So in another meaning, so they ask us to calculate all the parameters, starting by RC XM and R equivalent X equivalent and draw a corresponding simplified equivalent circuit. Okay, so let's solve it here directly. So okay, starting for example from the no load test. Okay, let's draw the circuit of the no load test. So this is the circuit of the no load test. We have only R equivalent RC that represents the core losses, and we have XM, the magnetizing reactance. So this is V1 or V0 indicates to the no load state, and here we have I0, RC and XM. RC and XM. So according to the data given, so here since we have a power, RC equals to what? RC equals to V square over, so RC according to the circuit, RC equals to what? Equals to V0 over I0, over IC, not I0, according to the circuit. IC, but here we don't have IC yet, so it's V0 over IC, and it's equal also to V square over P. R equals to what? RC equals to, so here they use directly the rated voltage 7,500 over a square over 180. So Okay. Seven 1,500 square over 180 equals to what? Equals to normally 300 12.5 kilo, because it's very huge, kilo on. Okay, this is RC. Now, since we have RC, we can measure IC. We can calculate IC. So IC equals to what? IC equals to V0 over RC. And it's equal to 7,500 over 312.5 kilo, and it's equals to 0. So I'm doing it by my hand. So it's 0.024 ampere. Okay, so in order to find XM, we need to find the IM, which is the magnetizing current. We know that I0 equals to IC plus IM vectors, IC square plus IM square. Okay, therefore IM equals to what? Equals to I0 square minus IC square. Okay, let's keep it here. Add another slide. Okay, so IM normally equals to 0. IM equals to 0.19 okay, 1999 or 1998. Anyway, so then XM is 1991. Okay. Then XM can be measured. XM equals to what? XM equals to V over IM, and it will be equals to 37.6 kilo ohm. Please check with me the calculation. Okay, let's check again. So 7,500 divided by 0.
That's it, sir. It's correct.
Okay, so that's good. So this is XM. Okay, so this problem is a little bit clear compared to the previous one. They done the tests in the same site, and they specify that it's a step-down transformer. Okay, now for short circuit test, we are going to calculate the equivalent impedance, resistance, and reactance. Okay. So using the measurement of the equivalent to the short circuit test, okay. Okay, so the equivalent, okay, so this is the second part. The equivalent equals to what? Equals to V short circuit over I short circuit, and equals to what? It's equal to V short circuit. V short circuit is 366 over. I need to print those problems over 2. Yes, over 2. So it will be equals to what? 366 divided by 2. It's 138 ohm. This is the equivalent. So R equivalent equals to what? R equivalent equals to P short circuit over I short circuit square. So it will be equals to what? P short circuit is 300 over I short circuit, which is 2, so square it's 4. So it's 75. This is R equivalent. Okay, now let's calculate X equivalent. X equivalent directly, since we have Z and R. So X equivalent equals to what? Equals to Z square, which is 138 square minus 75 square, and let's calculate it. 138 square minus 75 square. Okay, square root. So it's 166.92. Oh, is it clear? Okay, so those are the parameters. Okay, here in this problem, we are going to use that approximation to calculate, because they ask us to draw an approximate equivalent circuit. Yes, the parameters of the approximate equivalent circuit. So when we are in the approximate, we are using R equivalent and X equivalent. So if we are in the exact, we may need to find R1 and R2. Okay. So the circuit they didn't specify refer to the primary. Yeah, refer to the primary side. Okay. So if it's referred to the primary, so if it's referred to the primary, we have V1, voltage of the primary stay the same. We have R equivalent, or X equivalent, and R equivalent. This is the secondary. Okay, so the voltage of the secondary will be multiplied, sorry, AV2. And this one is X equivalent, and this one is R equivalent. Sorry, I'm drawing using the mouse, and especially when its battery is low. Okay, you will suffer with it. Okay, so this one is X equivalent, and this one is R equivalent. Okay, also the parallel branch, of course. since we have calculated them, we can add them, approximate, no problem. So this is RC, and this is XC, and you will write all the parameters. Okay, so if you have in the exam or they ask you to drive the equivalent circuit, you need to write all the parameters here. Okay, so since the circuit is referred to the primary, of course R equivalent equals to what? Equals to R1 plus A square R2, and X equivalent equals to what? Equals to X1 plus A square X2. Okay, so I will show you that approximation, that how they calculate R1 and R2. Okay, I don't know where in this textbook. Yes, okay. So here, look, are you seeing this, the textbook? Okay, so if an equivalent T circuit, okay, the circuit, the exact circuit, they call it also T circuit because it's shaped like T. Okay, you can call it the T circuit. So, okay, the value of an individual primary and the secondary resistance and the leakage reactances referred to the same side are usually assumed to be equals. Okay, so it's just an assumption. For example, if we have, okay, so we have R equivalent is 75. So R1 equals to A square R2. Okay, so we divide R equivalent over 2. Okay, R equivalent over 2, which is 75 over 2 is 37.5. Then we write as, for example, so if we divide it over 2, okay, let's do it here. So since R1, R equivalent is, okay, let's change the color, is 75. So we divide it over 2. Then R1 equals to 37.5, and R2, A square R2 equals to 37.5. Sorry. Then we can find R2 from the TURAN ratio. R2 equals to what? Equals to 37.5 over A square. A equals to what? So A equals to what? 7,500 divided by 480. So it's almost 15. It's 15. 15.600. So A square is almost 244. Okay, so divided by 244. Then 37.5 divided by 244, and it's equal to 0.5. 0.15. So this is R2. So, okay, be careful. Not R1 equals to R2. R1 equals to A square times R2. Okay, so this is the approximation, but it's still an approximation. Okay. So to have the exact measurement of R1 and R2, we are going to do a test called DC circuit test. I don't know why I forget it to add it in the lecture. Okay, the DC circuit test. So we can feed the transformer with DC. Then from those measurements, you use Ohm's law directly, because in DC we don't have the effect of reactance. Directly we can measure the resistance. Another method, which called direct method, we can use an ohm meter to measure R1 and R2 experimentally, of course. Okay, I think we can stop here. The problem still not solved. Our problem 9.